Hi everyone, thanks for joining the Sensor session, What's New with Contextual Sensing. My name is Rinku Sridhar and I'm a Program Manager on the Windows Sensors team. Today, I'd like to cover three topics. One, future strategy for contextual sensing APIs. Two, new APIs for motion sensing. And the third topic is remote sensing. So let's get started. So let's begin with the future strategy for contextual sensing APIs. This is a topic that we have got multiple questions from developers in the last several months. Last year at Build, we talked about deprecating the Lumia Sensor Core APIs. I would like to talk about two new contextual sensing APIs that we introduced last year before we go into the future strategy. There are two APIs, one activity detection and another one is pedometer. Activity detection is used to figure out the user's motion context. For example, is the user running or are the users walking or are they in a vehicle or on a bike or are they stationary without moving or is the device lying on a table idle. So these are the different activities that we support. This is very similar to the Lumia Sensor Core activities APIs. Using these APIs, you can build very powerful health and fitness applications, applications for navigations and maps, and it can also be used for power saving scenarios. The other API is pedometer, and this is equivalent to the Lumia Sensor Core steps API. It counts user steps, both walking and running steps, and it also tells you the duration of the active time the user has been in. If you don't have a wearable or an activity tracker, you could use your phone to track the number of steps and track your fitness goals. If you have a wearable or an activity tracker that you're using, you could use these APIs in conjunction with those wearables, and in case you forget your phone, in case you forget your activity tracker, you could use your Windows device to track your steps. So I'd like to use this opportunity to also talk about the two new things that we are adding, the July refresh. One is we are adding emulators for both activity detection and pedometer. So while you're developing, in case you do not have a device with these sensors, you could still use your emulators to develop and test your app. Another new feature that we are adding is location service will use the activity detection to make their GPS polling more efficient. So what they do is they figure out if the user is idle, that is if the phone is lying on the table and it's not being used. Using activity detection, you can determine that, and they do not keep polling for GPS if the user is idle. This, as you know, GPS requires a lot of power, so it's a very powerful power-saving feature that we will be introducing. Now about the future strategy. So at last year's build, we talked about deprecating Lumia Sensor Core APIs. So as you know, we have very similar equivalent APIs, the contextual sensing APIs, activity detection, similar to activities Lumia Sensor Core APIs, and pedometer, that's equivalent to the steps. We deprecated the Lumia Sensor Core APIs as of last year, end of last year. So our guidance to the developers is to start using our UWP contextual sensing APIs in future. These APIs will not only work on the Lumia phones, unlike the Sensor Core APIs. These APIs will be supported on all Windows devices, on desktop, mobile, or even IoT devices if the sensors are supported on that device. The Lumia Sensor Core app, the sample app that you can get from the store, has also been updated to use the UWP APIs. If you have any feedback on this, please do let us know. We are working with the developers who have used in the past the Sensor Core APIs, and they are switching to the UWP APIs. To name a few, it's one such application is MS Health, and Fitbit is another application that we are working to move to UWP APIs. I'd like to use this opportunity to talk to you about where you can find the settings for contextual sensing APIs. So you could go under Settings. You can find it under Settings and under Privacy here. So exactly where you would see Location and Camera, you can find Motion Settings over here. So users have two different options to control access to their motion data. Motion data is going to be on by default. So you could either go and use the switch to completely turn off the feature, or like over here, or you could decide to turn off the feature for just a few apps. So there is an app level toggle where you can turn it off just for the apps that you don't want these motion data to work. So there are two developer scenarios here. The first scenario is while you are developing these apps, you might want to check if your app has access to motion sensors. Another scenario is sometimes people change their access privileges, so you might want to be subscribed to be notified of any access changes. Now I'm going to switch to demoing the emulator, which is something new that we are introducing in the July refresh. So here I am going to demo the emulator for the new activity detection and the pedometer features. So this is the Visual Studio emulator you can see here. So what you see here is the emulator for the accelerometer, and you can select Activity tab here. For the demo purposes, I'm going to use Sensor Info, which is a diagnostic app. So I'm selecting the Activity tab here. So as you can see, on the left side, you can select whatever activities you would like to simulate. So I'm going to add walking, running in a vehicle, biking, and then stationary. So once you add this, you can add it just by clicking on it. Once you add it, select the confidence. So I'm going to select high and low values for all of these. Now we need to select the time in seconds that we want each activity to be. And I'll select 5 seconds so we can run this really fast. Now I'm going to simulate these different activities. And once we play, you will be able to see on the Sensor Info app, the activity will change. Here you can see for the first 5 seconds, the user is walking, and now it's switched to running because that was the second activity we added. And this third one is in a vehicle, so you can see that here. The fourth one was biking, so you can see the activity here. And the last one was, this is the symbol for stationary, which is the last one. So once this is played back, in case you are interested in saving it for future, you can save the test, and I'm saying test 5. This way you do not have to keep repeating the same, keep adding it every time. I'm going to load another one. So here I'm loading another test that I created earlier. And let's use this for looking at the demo, for demoing the pedometer. See here, the activities I added, the one that I loaded, has walking, stationary, and biking. I'm also going to insert another activity, which is walking, and having the confidence high here and time 5 seconds. So when I start playing it, you should notice if it is a walking, if the activity is walking or running. Actually, let me add a running here. Time in 5 seconds. Then you will be able to see the steps changing, and this cumulative steps duration here will also change. And you should also be able to see the step kind changing from walking and running. So playing it now. So you can see it's walking, and you see the cumulative steps changing here. It's becoming 522, 524. But now it paused because it's stationary right now. When you're biking, again, there are no steps, so it's at a pause, nothing's happening. But once it switches to walking, so it switched to walking, and you can see the steps, cumulative steps increasing, and now it just switched to running, so it's increasing at a much faster rate, and the step kind is running. You can also clear the activities on your timeline here. So that's the demo for the emulator. So if you do not have a phone or a device with these sensors, activity detection or pedometer, you can always use these emulator to develop your application and test it. The second topic that I would like to talk about is about the new motion sensing APIs. As you know, we have accelerometer is one of the sensors that we have. In the July refresh, we will be extending the accelerometer API to add 2 new sensors, both gravity sensor and the linear acceleration. So accelerometer contains 2 components. One is the linear acceleration, which is the external force that's acting on the device, and the other one is the gravity vector, which points directly towards the center of the Earth. So previously, the developers needed to filter out these components in case you wanted to have just the linear acceleration. So now we have separated both, and we have added 2 separate sensors here. So gravity sensor, as I mentioned, gravity points towards the center of the Earth. So it could be used to create applications, to calculate tilt better. It can also be used to create gravitational field maps, which could be used for inertial navigation systems. And the linear accelerometer, it's again, you do not have to filter out the gravity component here. So you could just get that external force that's acting on your device. So these could be used to sense any sudden changes. Especially, it's very useful in gaming scenarios, precise moments. Or you could also use it for if you have, let's say, if you have a photo application and you have a panoramic photo that you would like to develop, stitching together multiple photos together. These do not require the gravity force. It's much easier with these linear acceleration. Another new API is we are extending the orientation API to add the geomagnetic orientation API. This is very similar to our orientation API, and it outputs both the rotation matrix and quaternion, exactly like the orientation sensor. The difference here is it doesn't include the gyroscope. It's calculated using only the accelerometer and the magnetometer sensors. Gyroscope generally consumes much more power, so it can be another very power-saving feature. Also, if there are devices without a gyroscope, you can still get your orientation with just the accelerometer and the magnetometer. Next, I'd like to show you the SDK samples and also walk through the general sensor API pattern. So the first thing is our namespace. So make sure you're using the windows.devices.sensors namespace. As you can see, using the linear accelerometer and the gravity vector is very similar to how you would use an accelerometer. Here, getDefault returns the default sensor. So if no sensor is found, then it will return null. The next one to keep in mind is the desired report interval. So you might want to select a report interval that based on your preference, that is the sampling rate. So sensor will have a minimum report interval. So figure out what is that minimum report interval, and then based on that, you may want to set the desired sampling rate or the report interval for that. Again, it's very similar to how setting these for linear accelerometer and gravity vector is very similar to how you would do this for accelerometer. The next pattern is the get current reading. So this is used if you want to get the current reading of your sensor. You use get current reading. So you can poll and get the value. As you can see here, we're using the get current reading for the accelerometer, and very similarly, you would use it for a linear acceleration. You can get the current reading, and you get the XYZ values. Same way, both for linear acceleration and the gravity vector. So now that we know how to poll and get the current readings, let's look at another pattern. So using this, how can you actually subscribe and get reading changed events? So you can subscribe to reading change events, and this will only return when the value changes. Here's the event handler. Again, very similar to how you would use the accelerometer. So let's look at the event handler. So this is the function for the event handler. You can see that the sender is casted as the accelerometer sensor. And another thing I forgot to mention is, so there is a reading type, a new property that we added. So if the reading type is standard, then it's this accelerometer. If you notice that the reading type is linear, then it means the linear acceleration, and the reading type is gravity, then it's the gravity vector. And in this sample, we are using the same event handler for all of these, but you could always use different ones to do this. So now that we have walked through the code, let's just run this and look at the app. So I'm just laying down this tablet on the table. I'm going to enable all the three sensors: accelerometer, linear accelerometer, and the gravity vector. So right now it's lying on the table. So if you look at it, on the linear acceleration, you're not seeing anything because there's no other external force acting on the device. But look at the gravity. Here you can see the z value, because gravity again it points toward the center of the earth. You can see the c value, which is high but very low value for x and y. So now I'm going to tilt the device a bit. So you can see the values changing here. So when I'm tilting, you can see the gravity values and the linear acceleration value changing. So now we are at the third topic, remote sensing. So let's begin with what is a remote sensor. A remote sensor is a sensor that could be anywhere, but it's really not on the device that has your app. So this device could be a Windows device, or it could be a device that's not running Windows, or it may not even have an operating system. It could be a headless device without any UI. So there are different ways of remotely sensing. I'm going to talk about two primary scenarios, or let's just call it flavors, for remote sensing. One is these sensors could be on these things. There could be different types of sensors. For example, carbon monoxide sensor, a temperature sensor, a humidity sensor, or any of those sensors that you may find in a smart home. All of these sensor data needs to communicate to your Windows device. As you know, there are several different standards and several different network communication protocols, making it very hard for interoperability. Open translators to things. Microsoft recently announced this week open translators to things a new open source project on GitHub primarily to solve this interoperability issue. As a developer, you can now control any similar sensor or a device created by different manufacturers in a very consistent manner. Here, conceptually, you have a schema and a translator. A schema defines a device. It essentially has the basic methods for controlling a particular type of device. For example, for a lamp, it's turn on or turn off the switch. Then you have a translator. What the translator does is it essentially does translation between your schema and the thing or the device. So as a developer, you do not have to worry about how you would communicate between the thing and your app. It makes it very easy. For more information, visit opentranslatorstothings.org. The site and the link is in the additional information slide towards the end of this presentation. Now let's look at the next scenario. Here you will have the sensors on your Windows device, but your app is on the thing. It could be running Windows IoT Core. Imagine a Raspberry Pi running Windows IoT Core, and your sensors are on your phone or your tablet, and you would use those sensor data to control your thing. So this is an opposite reverse scenario. Again, Microsoft recently announced Windows IoT Remote Client to solve this problem. So let's talk a little bit more in detail. So Windows IoT Remote Client, the remote client is built into the Windows IoT Core. So you do not require any additional hardware for this. All you have to do is enable the remote client on your Windows IoT Core, and then get the app, the Windows IoT Remote Client app from the Windows Store, and then start connecting to your IoT device. So what it is essentially doing is it gives your IoT device, usually is a headless device, so it gives a display to this displayless device. And second, it is allowing you to remotely access your sensors on your Windows device. You do not need to write any additional code or anything as a developer. I talked about the accelerometer, linear accelerometer, gravity APIs, right? So you would use the exact same API pattern, get default, to return the accelerometer, and you get the accelerometer coming from this remote Windows device. It is that easy. Now I would like to invite Leo Amadio from the IoT team to demonstrate the remote sensing. Hi Lou, it's really great to have you here.
Oh, thanks for having me. I appreciate it. I brought a demo from our Raspberry Pi 3 launch that I wanted to show, which not only shows some remote sensing, but also a closed-loop control. Something that we've added to Windows is interrupts for IoT Core, so that you can actually process interrupts in your application. For this demo, what we're using interrupts for is closed-loop control. Are you familiar with closed-loop control?
I know a little bit about it.
Okay, well, for our viewing audience, what we're doing here is applying power to a motor and then measuring how fast it's moving in order to apply the appropriate amount of power to maintain a set speed. Most people don't realize that manufacturing differences can cause two motors that are otherwise spec'd to be the same to behave differently under the same amount of power being applied. What we have here is a DC motor, a gearbox, and a wheel. We're going to set the RPM through our UI to the motor, or to the wheel, and the motor is going to start spinning. And that motor is being driven by a motor controller, and the motor controller is being controlled by a Raspberry Pi using PWM, or pulse width modulation. When we then have a sensor on the output that we can turn on that is read by the Raspberry Pi in order to implement that closed loop control. So why don't we go ahead and demonstrate what that looks like. So first of all, what I'm going to do is I'm going to apply power without closed loop control turned on. Okay, and I'll do this from our UI here. Okay, so a nice slow 14%. So why don't you go ahead and take this rod and try and stop the wheel from spinning. Okay, so it's really easy to slow down that motor. We don't have the feedback enabled. Okay, release the rod. So I'm going to turn on closed loop control. Now what we're doing is we have a quadrature encoder attached to the output shaft of the spinning wheel. That encoder is firing interrupts into our application. Our application is responding by seeing how fast it's moving and then comparing against our set RPM. Okay, so go ahead and put the rod up against the motor. So okay, go ahead. So what you saw there was our application detected that the motor was slowing down and applied more power in order to maintain a set speed. Okay, so that's interrupts in IoT Core. Now what we have on screen here is an application that's actually running on IoT Core.
Oh, so is it running on this Raspberry Pi?
It's running on Raspberry Pi here. So that application is actually generating a UI. Now what we've introduced is IoT Remote Client, which enables you to take that UI and remote it to another Windows device, desktop, Surface, or a Windows phone.
This is really good because most of these IoT things, they don't have a display. This is essentially giving a display to a displayless thing.
Exactly. So what we're showing here is the same UI is being remoted from the IoT Core device.
How did you do that?
Well, what we have on Raspberry Pi is a service that scrapes the screen. We're actually using DXGI display duplication, which is an API that you can call from a native application. We scrape the output of the screen. So after all rendering is done, we pull the output back, we run it through an encoder, and then send it to our client application, which you can install from the Windows Store. That's called IoT Remote Client. Now, in order to enable that, when you install a IoT Core device, it's not on by default. There's some security implications of turning it on, so only do it on a closed network. What we would do is you go to the device portal, and the device portal you can access from our IoT Core dashboard. At the very bottom is the Remote tab. Clicking on the Remote tab will start the server. Once the server is started, then you can use the application to connect to our control.
So all you have to do is enable the remote client on the IoT Core and get the app from the store.
That's right.
The remote client. Awesome.
Now, once you have the client, there are two ways to discover on a tablet. One is from a discovery service where it'll enumerate all of the devices that it discovers, or you can manually type an IP address in. So here we're going to connect to it. Now, once it's connected, what we have is the display of the application running on the IoT Core.
Wow. I think the primary point here is, as a developer, you do not have to do anything extra. You could use the exact same accelerometer API and get these sensors on a remote device.
Well, that's the next point is the accelerometer that's on the Surface here can actually be remoted to the application running on IoT Core. Okay, so not only are we grabbing the display, but the sensors are actually projected. We're projecting magnetometer, gyro, and accelerometer. The same APIs that you use on a Windows phone actually work in IoT Core. So you call accelerometer get default, and you'll actually get the remoted accelerometer from the Surface here. Okay, and we have that by turning this on. You can see that as we it's a little loud, but as we tilt the surface, you actually are, yeah, there you go. Oh, it's turned off right now. Pretty cool, huh? So let's go ahead and shut that off. Okay, so what we've demonstrated here, not only is our interrupts handler in IoT Core for IoT Core applications, but also the remoting technology, both for display and input, as well as for sensors.
So before we end the session, I wanted to talk a little bit about the additional resources that we have. We have MSDN API reference for sensor APIs. I will also post periodic blogs on contextual sensing. You can search contextual sensing and our latest blogs would get returned. You can also go to multiple other build sessions, check them out on channel 9. I specifically want to call out one Windows 10 IoT core session from Maker to Market by Dan Rosenstein. So the remote sensing that Lou and I just talked about, you will be able to find out more from Dan's session. Also check out the open translators to things.org, where you will have much more information on how to remotely connect to the different things out there. Now the feedback part. If you have any requirements or new feature requests for us, please do let us know. Or if you have any other concerns or issues with the sensor APIs, definitely reach out to us. Thanks again for watching.